In this video, we will see how Newton's second law of motion is related to the Schrodinger equation in quantum mechanics. Let us first look at Newton's second law. It says that the time rate of change of momentum is equal to the force. Here, for simplicity, we are only considering one-dimensional systems. So there are only numbers and functions and no vectors. Now for a conservative force, we have a potential function, and the force can be written as negative of the spatial partial derivative of the potential function. Therefore, we can also write Newton's second law in this form, where the time rate of change of the momentum is equal to negative of the spatial rate of change of the potential function. In the quantum version of this law that we will derive, the momentum is replaced by the expectation value of the momentum operator, and the partial derivative of the potential is replaced by the expectation value of the partial derivative of the potential operator. This result is also known as Ehrenfest's theorem, after the name of the physicist who derived this result. So now our objective is to prove Ehrenfest's theorem, which says that the time rate of change of the expectation value of the momentum operator is equal to negative of the expectation value of the spatial rate of change of the potential operator. First, we will show that this result, the Ehrenfest theorem, is a special case of this more general result, which says that for any quantum operator O, the expectation value of this operator O, when we take its time derivative, the time rate of change of the expectation value of any operator O is equal to I by h bar times the expectation value of the commutator of the Hamiltonian operator and the given operator. So this is a more general result that we will derive, but first let us see how Ehrenfest's theorem follows from this more general result. So suppose in this general result, this observable O is equal to the momentum P, and our Hamiltonian is of this form: P square by 2m plus potential operator. Then if we take a commutator of H and P, then we see that this commutator is simply equal to commutator of the potential operator with P, because the kinetic energy part, P square by 2m, commutes with P. Now in position basis, the momentum operator is equal to minus I times h bar times the spatial derivative, that is the derivative, partial derivative with respect to the coordinate basis, and it is with respect to the position coordinate. So this is our momentum operator in position basis. And I'll leave it as a simple exercise to show that the commutator of the potential operator with the momentum operator is nothing but I h bar times the spatial partial derivative of the potential operator. This result is not difficult to show. The trick is to take any arbitrary function f and first act this function with the product vp. So we are first taking its partial derivative with respect to x, and then we are multiplying with v. Then with the same function f, we act it by pv. So we are first multiplying it with v, and then we are taking the partial derivative of this product function that we get, and then we subtract these two. Then we'll get this result, I h bar partial derivative of v with respect to x and times this arbitrary function f. So now we have shown that our objective, which was to prove Ehrenfest's theorem, it follows from this more general result. So now our new objective is to prove this more general result. For this, we first write down the expression for the expectation value of observable O. This is the expression. It is the inner product of state psi, where we are taking the expectation value of observable O in state psi. So this is equal to inner product of state psi with this state obtained by acting the given state psi with observable O. In most quantum mechanics texts, this is usually written in Dirac notation like this. In Dirac notation, the expression for the expectation value is written like this, where this observable is sandwiched between these Bra and Keat vectors. However, in some situations, for example, when taking derivatives, Dirac notation can be a bit confusing. So here I am using this more explicit notation for the expectation value. Now, when we take the time derivative, by the product rule of the derivative, on the right hand side, we get sum of two terms. In the first term, we have time derivative of the state on the left hand side of this inner product, and in the second term, we have time derivative of the state on the right hand side of this inner product. Now when we use Schrodinger equation, then the time derivative of state psi by Schrodinger equation can be written as minus I by h bar and h acting on psi. So by Schrodinger equation, time derivative of state psi is minus I by h bar and Hamiltonian operator acting on psi. So we replace this time derivative of state psi with minus I by h bar and Hamiltonian operator acting on state psi in both of these terms. Now we take out the constant factor out of this inner product, Hermitian inner product. When we take a constant factor out from the first place in Hermitian inner product, it gets complex conjugated. So in the first term, when we take out this constant I by h bar out of the inner product, it becomes it achieves a negative sign because of complex conjugation. So we get I by h bar, its sign is changed, while in the second place a constant term remains the same, it's not complex conjugated. So the sign of the constant term in the constant factor in the second term remains the same. So we get two terms differing by sign. In the first term we have h bar psi on the left hand side and inner product with operator O acting on state psi, and in the second term we have state psi and inner product with operator O times h acting on state psi. Now we make use of the fact that the Hamiltonian is a Hermitian operator. So inside the inner product, it can be moved from acting on the state on the left to the state on the right. So we now get two terms by using the hermiticity property of the Hamiltonian operator. We get two terms. In the first term we have HO, product of H with O sandwiched between states psi, and in the second term we have the product OH sandwiched between states psi. We combine these two terms and we get a single term in which the operator HO minus OH is sandwiched between states psi. And this expression is HO minus OH is nothing but the commutator of Hamiltonian H with O. And this expression itself is nothing but the expectation value of this commutator of H with O in the state psi. Therefore, the general result is proved. So here is the summary. We proved this general result, which says that the time rate of change of the expectation value of any quantum observable O is equal to this constant factor I by h bar times the expectation value of the commutator of Hamiltonian with the given observable O. And we saw that this general result implies a very important special case, which in one dimensions can be written as this equation, which says that the time rate of change of the expectation value of the momentum operator is equal to the negative of the expectation value of the spatial rate of change of the potential operator. And this result is the quantum version of Newton's second law, which says that the time rate of change of momentum is equal to the force.